Um, and once I'm done, I will download this recording and share with you on a drive. Um, so before I begin, I just want to first, tell you guys how to set up R on your computer. So in order to set up R, we need to download two things. So one is R itself, the software R, and the second thing is R Studio, which is a console or kind of a window where we can operate R. So in order to download R, if you this is R is free to download, so that's one of the great things about R. So you just go download R for Windows. Um, uh, if you have a Windows computer, R for Windows. I have a Windows computer, so I'll do that. If you can do it on your, if you have a Mac computer, then it has options for Mac as well. So this is download R 4.5 for Windows. Once you click on it, it will download. So I have already downloaded R on my computer, so I'm not gonna do it, but I want you guys to do it. Once you guys are done, just give me a thumbs up. And please, guys, feel free to interrupt me because I want to make this a workshop so that you guys can have a hands-on experience. I think Marwa should have shared a sample datasheet file with you already, where on which we will be working on. Has everybody downloaded R on their computers?
It's okay, Dr. Hamza. You can please continue.
Okay.
They'll catch
So
it.
okay, once we download R on our computers, we need to install that. And after we install R, you'll have something like this on your computer, if you can see this. So this is the icon for R. But this is the icon for R only, not for R Studio. Next thing we have to do is to download R Studio. So the same thing we'll do is we go on R Studio. So on this faucet, this is I think the company. So you download R Studio. So if you go down there, so R Studio for Windows, once you do that, it will start downloading here as well. So once you finish download, it's a quick download. You just have to install R Studio as well. Once you install R Studio, you will have something like this on your computer. Um, I'm gonna give you just a few seconds so that you can set it up and give me a thumbs up once you're able to do that. Marwa, should I continue?
Yes, yes, please. The most of them here, they are just here for the lecture, so they'll basically view it later on the YouTube and then they'll catch accordingly. So you just go on.
Okay. So once we download R, so we'll have this window in front of us. So this is the data input window where we'll write all our commands. This is the output window. This is the help window, or you will see some plots here. And this is the what you can say. This is your variable window where every variable, anything that you give to R will store it in this window. So before we begin, I want to just go over this sample data sheet with you that I shared so that you guys can understand a little bit about it. I know you have had lectures regarding how to collect the data, extract the data. So just a about a brief introduction about this data. So this is a meta-analysis that we did where we compared men and women in their outcomes when they had STEMI with shock. So number of men, number of women in hospital mortality, then 30-day mortality, stroke, bleeding, length of stay. Length of stay is a continuous outcome. So you have mean and ST and mean and ST. And then reinfarction, and then renal replacement therapy. So basically, you have every binary outcome has two columns for control and variable, experimental and control, and every continuous outcome has four columns with mean and ST for experimental and mean and ST for control. So once we are done with this, let's just go on. Now on this R, first thing we have to do is there are multiple packages on R where we can do meta-analysis. So there's metaphor package, there are X package, multiple. So the beauty of R is any researcher or any statistician who has good knowledge of R and wants R to run an analysis can develop a package and give this to R, and R will store it in a memory. And this is all freely available. This is all open source. So I'm going to teach meta package because that's what I am most accustomed to. That's most easy to implement, and that gives generally most of the results that we need here. A point to be noted here, meta package is when you do meta-analysis, there are two approaches to do a meta-analysis. One is a frequentist approach, which we employ usually. One is a Bayesian approach. So in this lecture, I'm going to talk only about the frequentist approach. So meta package is a very good package to run meta-analysis using a frequentist approach. So before we do that, we have to install the packages in our computer. So so the first command is install.packages. So when you download R, if you are going to write any prompt or any command, R will give you options, what options are available. So I just click on this, then it shows up install.packages. Then this in inverted commas, I write meta. After I select everything, I click run or I click all plus enter. So I can just, click run. So you see this here, this meta package is being downloaded. Now this command shows when you have this in the result window, it means that the package has already been installed. Now once we install the package, we have to load the package. To load the package, the command is library. So library again, but this time we don't need to write the inverted commas. So library meta, you select all this, and this starts to load the package. You see here, so this package has now been loaded. So now you have successfully loaded the meta package. Now, once you've done that, you have to first do a couple of things. You have to load the data which you are trying to, run meta-analysis on. So we have to what we essentially need to do is load this sample data set in our R. Before we do that, the best way I know to do it is to do this. Write a name for the data, whatever data that you want. So let's say me, I just want to name it as data. These are the sample data sets, so which R has, but we are loading our own data set. So we'll do this. Now this symbol which has you know a less than mark and a dash mark. So this less than and dash, it's an assigning symbol, which means that whatever I'm going to put on the right hand side of this symbol is going to be loaded or stored into this data variable. So just to give you an example, if I say here 2 and I load 2 and run it, so data will contain a value of 2. So this is just an assigning symbol. What I will do is now I will say data, whatever I'm going to assign this to the data, read.csv, and then I'm going to say file.choose. And then again, so basically what it's saying to R is, I want you to read a CSV file, which is a type of Excel file, a comma separated value file. And what file I want to use, I want to choose a file. So when you say file.choose only, so it will open up a dialog box. So it will open up a dialog box, which will say which file are you going to choose. It will a dialog box will open up. You can go into your computer just like in any dialog box, and you can choose the file. Now, what I'm going to do is I'm going to select all of this, and I'm going to say run. And again, a dialog box will open up. So when this dialog box opens up, I can just go and just choose the sample dataset for my desktop folder. So I chose the sample dataset. So you see, data now has 10 observations of 20 variables. So again, take a look at this file. How many observations does it have? So it has 10 observations, and there are almost, if you count them, there are 20 variables. So this dataset has now been successfully loaded in R. How to make sure that it is loaded? We can just use this option of view and just click data. So view data, we run it, and this is the data window that you will see, which shows that the data we tried to upload has already been stored in this data variable. All the values that were contained in that sample data sheet now has successfully been uploaded in R. Now we can play with this data sheet, and now we can run analysis on it, or we can run meta-analysis on it. Um, we can run calculations on it. Whatever calculation we want, we can run on it. Now, next thing we need to do is now we're able to run a meta-analysis in R. Now, there's a very a helpful function in R called help function. You can go into an R and you can type whatever help you want. So we need the help regarding meta. So even if you don't know the coding of something in R, you can just go to help and R will literally tell you the coding, how to code for it. So so this is the meta package and this is how to code. So you can either do this, or what I do here is I just say question mark meta and I just run this, and this again shows up the same thing. So let's just say I want to run a meta-analysis. Now I want to run a meta-analysis on this data. Now, before you run a meta-analysis, you need to know what kind of data you are working with. So the data that we have right now is basically uh, binary data and continuous data. So what is binary data? Binary data is something that's yes or no, um, true or false, one or zero. That's binary data. It's either yes or no. So hospital mortality, either you died or you did not die. So in the first study, you have 81 men, and out of 81 men, 29 died, and 60 women, and out of 60 women, 21 died. It means the rest of the women were alive. So this is a binary data basically. Again, 30-day mortality is a binary data. Stroke is a binary data. But if we talk about this length of stay, so length of stay is a continuous data, which is just like blood pressure, just like height, just like weight, which can be anything from 1 to million or more than that even. So this is continuously 1, 0, 1.1, 1.2, like this. So for this data, you need mean and SD, for both experimental and control. So let's talk about running a binary data first. So binary data, you need a meta bin function. You see this meta analysis of the binary data. For continuous data, you need a meta cont function, meta continuous. If you guys have any question, stop me and I will explain it further. So we need meta bin. So I can just click on meta bin and it will literally tell me the coding that is required for the meta, all the coding. We don't need to know all these terms, what these terms mean, but the major terms we need to know. So let's talk about meta bin. So I need to analyze, let's say I'm going to analyze this hospital mortality. So I would say in-house, let's say meta in-house mortality. So this is just a variable name that I've chosen, just like the data variable. Again, we'll use this assignment symbol. So whatever meta-analysis is going to be done, the values or results of those meta-analysis are going to be stored in this variable. Next, I choose meta bin, and then
मैंने इसलिए
uh,
यूज नहीं किया, मोबाइल से कर लिया था.
okay, the meta bin, and then we choose. So now we started to use codes for our meta-analysis. So I would say event dot e. So number of events in the experimental group. This is what it means. So one thing you have to make sure is to pay good attention to the symbols like commas and colons. If you don't pay attention, then you can miss some of these and R will return you an error. So I will show you what it means. So event.e. In this data set, let's say men are the experimental group. Then which of these columns would you say contains the events in the experimental group? So N is the total number of men in the experimental group. N is the total number of women, which is the control group. In-host.mort.men, which is the total number of mortality or in hospital deaths in men, which is the experimental group. So this is the column for events. And this is in-host.mortality.women. This is the total number of women who died, which is a control group. So event.e is in-host.mort.men. Just make sure you have whatever symbol, whatever column names are here, you need to write the same column names here and then comma. Then you have which says n.e, which is n.e, which is total number of patients or participants in the experimental group, which is n.men, n.men. Then you have event.c, which is again the total number of events in the control group. We already discussed. This is inhosp.mot.women. So we'll use that. And then we need n.c, which is total number of participants in the control group, which is n.women. Next, once we do that, then we need to specify the study label. So what is the label of the study? So here the label of the study is author.year, which is the name of the study. Author.year. And then it's gonna say what is the data you are using. So the data we're using is actually this data. The data. Then you have if there is anything to exclude, if there is anything to cluster. The next important thing is method. So if you go down to method, it will tell you what exactly is mean. So you have inverse variance, you have mental Hansel, Peto, GLMM, multiple things. Importantly, we use inverse variance for random effects. R uses inverse variance for random effects, and mental Hansel for fixed effects. So here I can use inverse. You have to type it the same way that's written here, inverse. And then comma. Then the next question is is summary measure. What is the summary measure you are trying to use? So the summary measure I'm using is it can either be risk ratio, odds ratio, risk difference, multiple other things. So typically, because if this is a meta-analysis of RCTs, I try to use risk ratio or relative risk. If this is a meta-analysis of observational studies, I use odds ratio. So here I'm going to use odds ratio. And the next option is incur. Incur is you can use it, you can not use it. I typically tend to use it. What incur does is if there is a value which has zero counts in it, what incur does, if there is a value with zero counts, R will basically ignore that there is nothing there. So in order to make sure R captures that, what you do is you give R gives 0.5 or whatever number you mention in incur into that value to analyze it, and once it's analyzed, it takes the same value which is given to it back. So it will give. So I will give zero. I will give 0.5, which means that 0.5 will be added to this empty cell, and then once the analysis is done, it will take the 0.5 out. Then the next step is you don't need all of these. The next important thing you need is random. Random is a logical variable. Logical variable is either true or false. So you can also either write as true like this, or you can just say t. So random is equal to t. And then you don't need the rest of the stuff. The rest of stuff is how to make forest plots or something. We'll discuss that later when we come to forest plot. So this is the basic coding of our meta-analysis. So once we select all that, we run it, it has run, and this meta-analysis is now stored in this meta in-host variable. So now just run this meta in-host variable and see what it contains. So this is the result of that. We have 9 studies. Even though we have 10 here, one of the studies did not have any variable, anything. So only 9 studies were run. So 9 studies were run. Total number of observations, if you say the total number of observations, if you in experimental control, if you add them, you will come out with this. Total number of events, if you add them, it cannot come out with this. Based on it calculated an OR with 95% confidence interval and a p-value. Using random effects model, it says OR is 0.7656 with 0.69 to 0.84, which means men as experimental group have lower risk have lower odds of having in-hospital mortality as compared to women. And this p-value is significant, which is less than 0. Which is significant. So if it's less than 0.05, it's significant. Then the next important thing is that you need to know is I square. I square, what it tells you is what's the heterogeneity. So if it's less than 40%, it's good. If it's 40 to 70%, it's moderate. If it's above 70%, it's high. So this has high heterogeneity. High heterogeneity, I'm sure you must have been taught in the previous lectures that if you have high heterogeneity, it means the studies are uh, the studies are variable. The studies are variable. It means that even though we are testing those, the methods that they use, the population that they use were were a lot of there was a lot of heterogeneity. They were not, a single unified population. Uh, and the next thing you need to know is this is the detail. So it's not inverse variance method and restricted maximum likelihood estimator for tau square, and it's calculation based on I square for Q. But important thing is that you need to know the inverse variance method. So we use random effects model, inverse variance method. Okay, now let's try to see what forest plot does it give us. So the formula for forest plot is you go like this, the same way we uh, went for meta. You run for forest plots. It's a metaphor package, meta package, because we're using meta package, we'll use this. So sorry, this one. So this is the forest plot. This is the forest plot for meta package. So what we need to do is the simple way to do this is to just forest and meta in host, whatever meta we did. You select this, write this, and it will give you a forest plot. So this is the forest plot. But this is not a very good forest plot. So let me just open it up in a better way. You can open it up. So this is the forest plot that R has given you. The same information that you have in this results window, you have in this window, 0.77, 0.69, 0.84, rounded off, you see it here. You see that it's significant. That's why the diamond does not touch the line of no significant line of, like line of one. You have heterogeneity 96%. It has given you everything. Random effects, common effects, it has given you everything. Marwa, what's happening there? I don't know what's going on with the computer. Somebody did something.
I'm not sure. Just continue. I think if it's not bothering you, it's
Okay,
fine.
okay, okay. I think somebody tried to write something on the screen. Anyways, okay. Anyways, so let's just continue. So we need to fix this meta forest plot a little bit. So how to fix this? One thing I tend to do is mention what is the experimental. So label dot e, which is what is the label that you're going to put for experimental. So I would say experimental group is men. I would just say men. Okay. Then label dot c, which is what is the control group. I would say woman. So if I do this and run, you see it has now changed it to men and women. So basically, this is now gives me a little bit more information. Um, what are the names of experimental and control group? Then the next thing we need to do is which side of this forest plot favors what. So does this side favor experimental group, or does this side favor a control group, or does this side favor experimental group, or does this side control group? So we need to know. So in order to judge that, you have to first understand what is the nature of the outcome that you're using. Is it a good outcome or is it a bad outcome? So mortality, dying is obviously not a good outcome, it's a bad outcome. But procedural success is a good outcome. So uh, if men with experimental group has less of a bad outcome, then it means everything on the left side of this forest plot is favoring men because it's a bad outcome. The less you have is better. So label dot left is favors men. On the other hand, label dot right is actually if so if women had less number of deaths then and men had more number of deaths, then this diamond would be here. So if the forest plot is on this side, then it means this side favors women. So less of a bad outcome in experimental group means this side favors experimental group. More of a bad outcome in experimental group means this side favors sorry less of a bad outcome in experimental group, this side favors experimental group, and conversely then this side would favor the control group. So the right side favors women. Now let's run this and see what it shows. So you see this, it says favors men and favors women. Now what if it's a procedural success? If it's procedural success, then you need more of it. It's a good outcome. So then if experimental has more of an outcome, then the odds ratio for that, let's say if something that you want in men, so procedural success you want in men, then if it's good for men, then it would come here. It would be on the right side. The then the labeling would switch. Then you have uh, favors men on this side and favors women on this side. Does anybody understand this? This is a little tricky point. Does everybody understand this? So just to summarize, if you have a good outcome, then right side favors the experimental group. If you have a bad outcome, then the left side favors the experimental group. Simple as that.
Sam, Sam, Dr. Hamza, can you please repeat that one? Favors men and favors women.
Yeah. So if you have an outcome which is a bad outcome, let's say we talk about mortality. Dying is obviously a bad outcome. Bleeding, stroke, hospitalization, they're all bad outcomes. If you have a bad outcome, then you, if experimental group has more of a bad outcome, then it will be in this side, on the right side of the forest plot. If experimental group has less of a bad outcome, then it should be on the left side because the ratio is experimental divided by control. So if you have experimental, which is more bad outcome, the ratio would be more than one. If you have less of a bad outcome, then the ratio would be less than one. So in this particular example, men have less of a bad outcome, which is mortality. So it means that the left side of the forest plot favors men. And conversely, the right side would favor the control, which is woman. So just to keep it simple and simple and clean, if you have a bad outcome, then left side favors the experimental group. If you have a good outcome, let's say procedural success, then right side favors the experimental group. Does that make it clear? If procedural, so depends upon what procedural outcome you're talking about. If the procedural outcome is procedural success, then it's a good outcome. If the procedural outcome is procedural, like access site complication, which is a complication, is a bad outcome. So you have to understand what outcome you are, clinically, you have to understand what outcome you are assessing. Is it a good outcome or a bad outcome? Procedural success is a good outcome. But procedural complication are a bad outcome. So bad outcomes, the left side favors the experimental group. The good outcome, like success, then right side favors the experimental group. And conversely for the control group. Next, the last thing if the procedural success is low in men, then if the procedural success is low in men, then the diamond would be on the left side, but the left side is not favoring men. The right side actually favors men because you want more on the right side. So if that's the case, let's say if we talk about procedural success, let's say this diamond is procedural success, then you have to say the left side then this is what you'll have to do. Then you have to mention it yourself. If this was procedural success, if this was, forget about if this is immortality, if this was procedural success, you need more procedural success in men, but you get less procedural success. It means that men have bad outcome because procedural men have less procedural success. Men have less procedural success, which means that this particular thing that you are studying is not favoring men. So the favors men would come on the right side, even though the procedural success is low in men. Because procedural success itself is a good outcome. I know it's a little bit confusing, so let me just rephrase it. Procedural success itself is a good outcome. You want more of it in the experimental group. If if it is less in the experimental group, then it means that that particular procedure favors the control group rather than the experimental group. So this would be favors the control group. On the left right side, it would favor the, if it's a good outcome, then it would favor men here. And you have to judge it yourself. That's what I'm trying to say. I hope that's clear. Okay. So next what we'll do is one thing I tend to do is I use this column called all studies, which and F. So you see in this image, you have all the studies which 10 out of 10 studies, but you know that only 9 were analyzed because one was not analyzed because it has no data. So this basically has no weight in the forest plot, 0% weight. So I typically tend to remove this study to make things clean. So what I'll do is I use all studies is equal to F. So what I'm telling R is not use all the studies, only use the studies which actually are used to make analysis. So I would run this and this last one would just go away. So this is what I do. So now you don't see the last one. So now you have this forest plot, which actually gives you quite useful information. It tells you what is the experimental group, what is the control group, which side favors the experimental, which side favors the control group. You have the random effects model, you have heterogeneity, and you have all the numbers of all the events in all the studies. You can also use some other thing. If you don't like this forest plot, then you can use this. Let me see. So you can use this. You can change the layout. So one of the layouts that I typically like to use is you say JAMA. So it will use the layout of JAMA, how JAMA likes to present its forest plot. So this is the way JAMA presents its forest plot. Another way you can use it, you can also use RevMan, and you can use this and it will give you the forest plot the way RevMan prints forest plots for you. So this is the style of RevMan. You can use multiple things. You can change, another thing you can do is if you go to this forest and you go through these commands, it will give you a way how to change colors, how to fill colors, how to separate the columns, left column, right column. So you just have to go through all this. I don't think so I have time to go through all of this, but you can go through all this and you can just tweak your forest plot the way you like it to do. R has a lot of another thing you can do is if you don't want the common effects, so you say common is equal to false, and it will not print out the common effects model. So you see, it won't give you the common effects. It only gives you the random effects. So some journals do not like the common effect. They say, just clean things up. So it will only give you the random effect. So you can do all those things with R. So now what we have done is we have done a meta-analysis on binary. We have made a forest plot. One thing we need to do is we need to do testing for bias. This is important, which is called meta bias. We need to see if there are any bias, a publication bias among the studies. So this is the meta bias, coding for meta bias. And so let's just say I just need to know the p-values where this is there bias there or not. So I say meta bias. I'm not assigning anything. I'm just running an analysis. Um, then X basically, which means that what is the X here means the uh, you know which says if you take a look at object of class meta. So in our study, meta in house is an object of class meta. So we see meta in house, and then you have to say what is the method dot bias. What method you are using to test bias. So most commonly use it Eggers, but you can use other tests as well. So if you go to method dot bias, so it will give you, binary outcomes. You can use Harvard, you can use Begg, Egger, Thompson, you can use McCaskill, Peters. If you want to do continuous outcome, Shannon mean difference, multiple tests. So the most commonly used is Egger. So I'm just going to use Egger. The next thing you need to mention it is K-min. You don't need to do plotted correct. K-min is what is the minimum number of studies. Typically, you need to have 10 studies. If you have the less than 10 studies, then bias testing is not that great. It's not that reliable. But here we have 9 studies. If we do 10 here, then it won't give us any result because it will say that number of studies is too small. So if I do K-min is equal to 1, let's just say I want even one study to have bias, it will give me bias which is 0.661. So which means that it is not significant. Typically, it means that there is no bias in the study. Next, what I want to do is I want to create a funnel plot. So funnel plotting easy. I just use funnel and meta in-house. What my object for meta-analysis was, and I just run it, and it will give me a funnel plot. So even this funnel plot, you see there is very little, the scatter is kind of equal. It's not completely equal. It's kind of equal. And mathematically, this bias testing would tell you whether there is funnel plot symmetry or not. So this test is funnel plot asymmetry. There is no asymmetry, which means there is no significant publication bias. So once you have done all these things, you have basically done a meta-analysis for one outcome. There is one more thing that we have left to do, which is to test for heterogeneity. So in order to test for heterogeneity, we need to, so you know that when we did the analysis, we had like 96% heterogeneity. So we need to know what study is contributing the most to heterogeneity. So the way to do is what you can use something called meta-inf. Sorry, you can use something called meta-inf, which is influence analysis, and you can do meta-in-house. And what it's basically going to do is it's going to run the analysis by taking one study out and do the analysis of all of them. Then it's going to take the other study out and then another study out. So basically leave one out analysis. So it will rerun this meta-analysis multiple times, but each time it will remove one study out of those 9 studies. So if we run this, so you see this. So now it omitted Kundian and the OR changed definitely, and the I square is 97. So even if we remove this study, there is still high heterogeneity. If a study is contributing the most to heterogeneity, omitting that study will decrease the heterogeneity. So among this, I think the only study which decreased it to a little bit is Yakub. So omitting Yakub decreased heterogeneity to 89%, but still there is very significant heterogeneity. So I can say that all these studies together contribute significantly to heterogeneity. There is not one study you could say, okay, this is the culprit. All these studies contribute highly to heterogeneity. So this is a leave one out analysis. What you can do, sometimes if you have a study with high heterogeneity, the publishers ask you to run an influence analysis or to do subgroup analysis or whatnot. So this is the kind of influence analysis you can do to find out the culprit. If you don't find the culprit, just report to your reviewers this results of this test and say all the studies contributed highly to heterogeneity. And if the reviewers But if there is a if on the other hand, let's say if you find a study, let's say if Yakub et al. Decreased heterogeneity to, let's say, 39%, it means Yakub et al. Was significantly causing heterogeneity. Then you have to go into Yakub, read the study, and find out what it did differently than other studies. Was the population different? Was the method of analysis different? Was the method of checking what are the cases, what are the controls different? Something Jakub must have done that would have led to high heterogeneity. And once you omitted it, the heterogeneity fell down to almost no heterogeneity. So so this is the basic meta-analysis that we do when we run this. Now, do you guys have any question before we go on to the last topic of today, which is to done the continuous meta-analysis? Okay, let's just continue with the continuous meta-analysis now. So as I said to you before, so one thing I want to tell you in R is you can try to, one thing I find it very useful is using this these hashtags. So hashtags basically tell R to, this is just for us. This is commenting out. We are commenting it out for ourselves. R will just ignore this. So if I say binary meta-analysis, so basically what it does is if I save this, so you can actually save your coding sheet for R to use it later. So let's say if you run an analysis and the publishers ask you, okay, this is a problem, we want you to rerun the analysis. So last thing you want is not to save the coding sheet, then you'll have to go back and code the whole thing again. So you should save your coding sheets. And while I'm doing that, I just comment out so that to remind myself when I'm reviewing my coding sheet, what I did there. So meta-analysis, binary meta-analysis of in hospital mortality. This way, R will not read this. This is just for me, for my own knowledge, for my own remembrance. So what I will do now is I will just do this binary. Now I will do the continuous meta-analysis of length of stay. This is what I will do. So now I need meta cont. So I did meta cont, the same thing I did with meta bin. I so let's just take a look at the data first. So the data is loss dot men dot m is mean. Men, of course, is the experimental group. So this is the mean of experimental group. This is the SD for experimental group. This is the means for control. This is the ST for control. So this is what we need. So mean of experimental, mean of ST for experimental, mean of control, ST for control. And NE is the total number of patients in experimental and total number of patients in mean, which is n dot men and n dot men. So we have almost everything we need. So we'll just say meta loss. The same thing we did here with meta in-host, meta loss, assigning variable, and meta cont n dot e is equal to n dot men. Then mean dot e is equal to, what is the mean dot e? Let me see. Loss dot men dot m. Loss dot men dot m. Then st dot e is equal to loss dot men dot st. When I try to name these variables, I try to name in such a way that it will be consistent across all the outcomes, so that it's easy for me to it's easy for me to code for them. Then I have n dot c is n dot woman, and mean dot c is loss dot woman dot m. Then st dot c is loss dot woman dot st. Then stud lab is already the same thing, which is author dot year. I'm just going to copy paste this. Then data is equal to data, because this is the data we are using. We just named it data. And then the next one is method dot mean Um, how you are going to assess the means. So I use this LUO1. I think there is only one. And then method dot SD is equal to SHI. These are ways to um, assess the means and STs. And then you need summary measure. Summary measure, what summary measure are you using? Summary measure, you go. So this is important. What's the summary measure? So summary measure is mean difference, standard mean difference, or ROM. I don't know what ROM is, but typically I use standard mean difference, which is so mean difference. It just gives you the mean difference, which was experimental minus control. That's the difference of means. Standard mean difference is it weighs the mean difference based on the strengths of the experimental or the weights of the experimental and control group. So I typically use the standard mean difference. And the last thing we need to do is to use this variable method.smd. What is the method that you're using to calculate the standard mean difference? So typically there are two used very common. Hedges D is the default or Cohen's D. I use Hedges D most commonly. They all have their own, pluses and minuses, but you can do either of them. And then we need to mention again incur. Again, I'm going to use 0.5. Then random, which is true. Now, this is um, my basic coding for the continuous meta count. The rest of the stuff, you typically don't need it to analyze a continuous meta-analysis. So let's just see how it goes. So now we have the meta-analysis of meta loss here. So just take a look at the meta loss now. So you have two studies only. You have two studies. Only these two studies have length of stay mentioned. The rest of the studies have no length of stay mentioned. So we continue with these two studies. And this says SMD is 0.34. So it crosses the zero. So one thing for OR and RR, they are ratios. So if experimental is equal to control, then the answer for that ratio would be experimental over control is equal to 1. Then 1 will be the line of no difference. N dot men is not the number of men, it's the total number of patients in men. Uh, but SMD or mean difference is a difference, is subtraction, is experimental minus control. In that case, if experimental is equal to control, the answer would be 0. So 0 is the line of no difference. Okay, so if this whole thing crosses 0, then your p-value should not be significant, which is the case here. And again, it's the inverse variance method. Hedges D is used. So it's bias correction standard mean difference using that formula. So that's what it is. Now I'm gonna make the forest plot. So to just make life easy for us, I'm just gonna copy paste this here, and I'm just gonna copy paste here. So forest is meta loss. Label of E is equal to men because men are experimental. Label of C is women because women are control. Now we'll talk about this label dot left or right again. As we spoke earlier, anything that's bad, if it's less in experimental group, then anything that's bad, if it favors the experimental group, then it should be less in experimental group. Then it should come on the left-hand side of the forest plot. So length of stay is actually a bad outcome. You don't want your patients to stay in the hospital for too long. The more length of stay, the bad the outcome. So in men, if men have good length of stay, then it should be less than women. It should be, so men minus women should be less than 1, should be in negative. So it should be the left side. So label dot left should continue to favor men. Left side will continue to favor men. Right side, again, conversely, would favor women. And we don't want common effects. We don't want all studies. We want only the studies we discussed earlier. So let me just run this. And this is your forest plot. The width of this diamond tells you that it crosses 0, line of no difference, and it's non-significant. and it gives you heterogeneity, which is 100% heterogeneity. Now, so we have made the forest plot of that as well. Now, last thing, let me just make up the funnel plot of this, which is meta loss, which is the funnel plot. You see this completely weird funnel plot. Now, let me try to run the bias testing for this. I'm going to use Eggers. I'm going to use the same thing. K-min is 1. So K-min, it has not run it because you need at least 3 studies. You cannot do a bias testing for 2 studies. You need to know where the third study lie. Does it lie here? Does it lie here? How? Because then how would you assess the symmetry of the forest plot? You cannot. So this data is so insufficient because the nature of the studies that have been done on this. It's not out of your control. There are no studies for this thing. So the data is insufficient to run bias testing for this. So that's what it is. And again, if we try to run this influence analysis, it will also not come because what influence analysis does is it takes 1 study out. So out of 2 studies, if you take 1 study out, you cannot run a meta-analysis on 1 study only. So if you do this, it will again give you sorry, this is meta loss. So let me see. This is actually, you see this. So all the studies of 0.4763, 4670, basically, they are not even counted here. So these are the 2 studies that are being counted here. One, this one, and I think one, the, so it's Vallabhbhai and Yaqub. These are the only 2 studies here, and these are the only 2 studies involved. The rest of the studies basically the same thing. So basically, it's not running any influence analysis. So this is not a correct influence analysis that has been run. Even though sometimes the software runs something, it doesn't mean that it's appropriate to run something just because the software runs something. You have to use your knowledge of statistics to see whether it even makes sense. So if you have a leave one out analysis, you have 2 studies, you leave one out, the what are you going to run? You cannot run analysis on the other study. So that's why this influence analysis is basically nonsensical. You will not report this. So this is the overall meta-analysis that we run. Now, let's do a little bit troubleshooting. Let's say if I miss any of these, for meta, we can use 2 studies only. You can use 2 studies to run a meta, but in that meta for 2 studies only, you cannot run a bias testing, you cannot run an influence analysis. You can run a meta, like I ran a meta, we have a forest plot, but you cannot, further, do heterogeneity testing or other things. So it has 100% heterogeneity. There is no way of knowing where heterogeneity came from because the number of studies is just too small. The data is so insufficient that you cannot run it. So let me just do a troubleshooting. Let's say if you do this and if you miss a comma or something, it will then not run it. It will give you an error. The unexpected symbol in this. Basically, it says that there is an unexpected symbol. I don't know what it is. So basically, you missed a symbol, it will give you an error. So you have to be careful regarding that. And the same thing, if you miss out a symbol here, sometimes R gives you an error message like a small cross here, which will tell you that this is inappropriate. So the same thing, it is giving you an error message. I think this is just the basics of meta-analysis. What you guys need to do is make your own data sets, run your own analysis, practice yourself. You will make a lot of mistakes initially, but keep this help function in handy, and it will tell you where you made a mistake. And just keep on correcting mistake, and just practice makes perfect. So you just need to practice, and eventually you will be able to run meta-analysis on your own. Any questions now? Coding knowledge. I mean, when I started R, I never had any coding. I had no knowledge of coding. But when I started to run meta-analysis, I basically what I did right now, I just knew basic syntax, and I just used this help function a lot, a lot. So using this help function, I knew what mistakes I'm doing, how to fix those mistakes, and eventually it's a learning curve. Eventually you will get a hang of it. So I think uh, if you guys don't have any questions, I can stop recording. Marwa?
Um, yeah, Dr. Hamza, you can stop recording now. Everybody, if you have any question, you can ask Dr. Hamza now.
So network meta is a whole different ball game. You need to have a it's a net meta package, and it's a completely different, say it's a ball game. I mean, its coding is different, its analysis is different, its concept is different. So we can sometimes do that in a future lecture, but I don't think so. I mean, in 1 hour I can cover both meta and net meta together. And before you go to delve into network meta, I encourage you to practice this so that you are able to run this by yourself, and then you can jump onto the network meta.
Assalamu alaikum, Dr. Hamza. Thank you
Sound
so much for the wonderful presentation today. I have a question. Are there any resources for learning about the coding language? Because
Yeah.
the stud lab or those things, anything that is short and handy and we can learn something from.
So
Thank you so
typically, if you
much.
so typically if you see this, it tells you everything. So stud labs optional vector for study variables. It tells you this. Okay, and if you go down in this help section, it explains everything. Like what does a variable mean? It will give you examples down there as well. So typically, this help function is very handy. It will give you a syntax. It will tell you what every term in this syntax means. You can also sometimes subgroup. So let's say, let me do this. I think I missed one thing. So let me just do this. Let me just edit my plot in a way. Um, Let me say subgroup, or let me say subgroup, and I'm just randomly giving subgroup A or B. Okay, I'm just randomly giving it. I'm just telling you how to subgroup for this. So let me just add this, load this data again. So now I have loaded this data and view. So now this subgroup column is here. So I just want to subgroup it. So I can just do this and verse, and I say subgroup, and subgroup variable is subgroup because this is the name of the variable. And I just run this meta and host, the same variable, and now you will have subgrouping. So it will subgroup for A, subgroup for B, and when I make a forest plot, it will give you forest plot with respect to the subgroups. So you see this subgroup A, subgroup B. So just wanted to tell you this. But anyways, but regarding coming back to your questions, this help function is very handy to tell you what to do, how to do stuff. And if you want to have a resource, so um, there is a book called from Matthias Herrer. Let me see. So this is a book by Matthias Herrer. This one, doing meta-analysis with R. So it's a hands-on guide. It can tell you how to do stuff. So I actually this book helped me a lot. So doing meta-analysis with R. So hope that answers the question.
I think
Raza is asking, does the coding knowledge you taught is enough? So this is the basic coding for meta-analysis. So with this coding, you can majorly run majority of the meta-analysis that you will encounter. But if you want to run, complex meta-analysis, so meta-analysis is, there are multiple types of meta-analysis. There is binary meta-analysis, continuous meta-analysis, prevalence meta-analysis, mean, meta-core, and also there are multiple packages of meta-analysis. There is network meta, there is diagnostic meta. So meta-analysis has its own complete world. I cannot, give you the complete details about all the every different types of meta-analysis I did. This is the basic thing that I learned, and then I built upon this. So this is what I would encourage you: practice this, and then build upon this. Um, can you just open the R from start. I want to see its setting. Okay, so first of all, I told you that you need to download R and you need to download and install R, and you need to download and install R Studio. Once you do that, then let me just uh, close it. So this is our close it, and this is how it will open up. Um, so this is, I think, something a data that is saved already uh, in my. So this is how R will open up. If you open it for the first time, so it will show you. It will be like this. It will be clean. Everything will be clean like this. Sorry, like this. So this is the command window. This is the results window. This is the help window, output window. This is the variable window where and environment where everything, history, environment, connection, tutorial, whatever variables you are telling are will stored in this window. So this is the window of R. Okay. Does anybody have any more questions?
Okay, I guess that's it. Thank you so much, Dr. Hamza. It was such a comprehensive and a detailed session, and I think all of us have learned a lot of things from today in a very simplified way. Thank you so much for your time. I guess we have no questions left. You can stop the recording now.